So, welcome to everyone who's joined. I know that possibly there will be a few more people joining a bit later, but we should probably get started now to give the speaker enough time to give his talk. So this is the Turing Causal Inference Interest Group seminar, and I'm very pleased to be able to welcome Dr. Santtu Tikka. He's a postdoctoral researcher at the Department of Mathematics and Statistics at the University of Jyväskylä. So currently, he works as a part of the thematic research area of decision analytics, and his main research topics are Bayesian methods and causal inference. So in his research, he has worked on identifiability algorithms, as well as extending causal inference results to alternative causal models. So he's developed quite a lot of very impressive open source software packages for causal inference and simulation. So for today, he's going to talk about causal effect identification from multiple incomplete data sources. So over to you, Santtu.
Thank you, Max. So today's talk is actually based on two papers that are joint work with Juha Karvanen and Antti Hyttinen. The first one is actually the latest of the two, and it's a bit more, I would say, easier to understand, so I will start with that. And the second paper deals with context-specific independence, which is one of these kind of extensions to the standard causal modeling framework, or the structural causal models. So what this paper is about is essentially the data fusion problem, which refers to the scenario where we have multiple sources of data that are somehow different. So on the left, number one, you can see that this is the typical scenario that we are dealing with the ID algorithm, that we just have some joint distribution of some variables. And then from that, many extensions have been built. For example, we may have some experimental data, biased data, or data from dissimilar populations. And as a result, you could say that in these many different scenarios, we have a lot of different identifiability algorithms. So usually when there is some specific problem, some specific assumptions or distributions, then there's going to be a specific algorithm about that particular problem. The question we deal with in the first paper is that could we actually describe all of these individual cases as special cases of a larger problem? And we call this larger problem the general identifiability problem. So now, instead of a single distribution or some structured collection of distributions, we're going to have a set of arbitrary, interventional, or conditional, or just marginal distributions. And the task is to identify some conditional or just an interventional distribution from this information in the causal graph. And of course, when the set of information is general, then none of these specialized algorithms are going to work, like the ID algorithm. But what we can always do is just apply DAGS calculus. And the way we do this is using a search-based approach. And here's some further motivation why you might want to do this. The first one I already mentioned is that we have highly specialized scenarios and highly specialized algorithms. But there are some problems where we only have graphical criteria, which kind of makes it even harder to get the result you need, because you have to either apply the criterion by hand or develop some algorithm that essentially applies the criterion. Now, another thing is that sometimes these even specialized algorithms may not be complete, so they may not be able to solve every problem. In some cases, when we may have no results at all, meaning no algorithms or graphical criteria. But of course, we can always use DAGS calculus. And some of these more general cases have been conjectured to be NP hard, which means that there may not be nice, efficient algorithms for these particular problems. Okay, so the search-based approach that we constructed, we call it DoSearch, because it basically just applies DAGS calculus, starting from the known distributions with the goal of identifying the target quantity. And we do this as a forward search. So we start from the information that we have, so the distribution that we assume known, and we use the rules of calculus to just derive identifiable distributions until we hit the target or we exhaust the search space. Now, this is a very naive approach, of course, so to make this a bit more feasible and faster, we are going to do some tricks to basically reduce the search space. And another thing we can do is to use a heuristic. Basically, what we did was we tried to imagine how a human might apply calculus in practice, and based on that, we prioritize some distributions over others. And it works the same way as any other identifiability algorithm. If we find or manage to identify the target, then we're going to get a formula in terms of those distributions that we assume known. One nice feature of this approach is that this is going to be a sound and complete algorithm whenever calculus is complete for that particular problem. So here's an example in a very basic backdoor type of scenario. So on the left, you see the causal diagram, and on the right, you see this kind of a diagram of the path that the search might take when identifying this causal effect of X and Y in this case, in this graph. So on the top, you see that it's going to start from the joint distribution. It's going to derive the marginal of Z and the conditional distribution of Y given X and Z. And then it's going to use the rules 3 and 2 of calculus to identify some interventional distributions. Then it's going to use the product rule to merge them together and finally marginalize and get the causal effect. And you just get the normal backdoor formula for the causal effect. And now if we go back to this table, we can kind of say that we have this new line here, generalized identifiability, and all of these problems above it are essentially special cases of this generalized problem. But now there is one column here that I didn't mention yet, which is this missing data pattern. And this is something that we also wanted to consider. So how would we actually incorporate missing data into this whole framework? Because none of these algorithms in this table actually deal with missing data in the most formal sense. But this is actually something we can do because in a structural causal model, we can essentially extend it to capture missing data mechanisms. And the way we do this is that we add 2 new variables for each variable or vertex in the graph. So we're going to have proxies denoted by an asterisk and a response indicator. And the way this works is that we connect these proxies to the true values using the missingness mechanism. So basically, if we observe the variable, then the proxy is going to be the same as the true value. And if we don't observe it, so if the response indicator is 0, then we have a missing value or NA. Nothing more complicated than that. And what this means is that typically, if we're dealing with missing data, then we don't actually have access to the true values, but instead we only have access to the proxies. And even then, we may not be able to essentially recover the true values or the marginals of the true values, which we typically would assume known in a standard causal effect identifiability scenario. But fortunately, we can extend the search by essentially adding just a couple of new rules which have to do with this missingness mechanism. So we can enable or disable the mechanism and switch between the true values and the proxies. So here's an example what this missing data really means in this causal context from a case control design point of view. So basically here we have a study or randomized controlled trial where the inclusion into the study depends on the disease endpoint. So the response indicator RY is going to depend on Y. And we are only going to measure the risk factors denoted here by X from those that are actually in the study. So those for which the indicator of Y is equal to 1. And otherwise they're going to be missing. So the causal diagram looks like this, quite simple. And as you may know, in this case, if you only have access to the proxies of X and Y, then it's not possible to identify either the conditional of Y given X or the causal effect. But if we know the prevalence in addition, so the marginal of the true values of Y, then we can actually compute the causal effect. And this is the formula we get if we use this search-based approach in this problem. And what's interesting about this missing data in causal inference is that it's essentially or fundamentally a causal inference problem. Because even if we are dealing with just identifying or recovering the joint distribution of the true values, then there are scenarios where you really need to calculus. You cannot identify this marginal without it. And you can find examples from this paper by Mohan and Bird. Okay, so now we can once more reassess our table, where I've added some new or restricted algorithms for these missing data scenarios, which essentially operate just to recover the joint distribution or the marginal distribution of the variables. So no causal effects essentially. But now all of these problems essentially fall under this problem that I here refer to as the generalized identifiability problem with missing data, which can be analyzed by do search. But one unfortunate feature relating to this problem is that we know for a fact that do search is not complete for this problem. So there are some problems that involve missing data that cannot be solved with using do calculus alone. You need some additional tricks for that, which is kind of surprising because that's probably not true for any of the other problems here. Okay, so now I'm going to move on to the second topic, which is context-specific independence. And this is essentially simply just an extension of standard conditional independence. But it just means that instead of the conditional independence holding for all values, it's just going to hold for a subset of the sum of the values. So there are some values where the variables are independent under the condition, and on some they are dependent or independent. Now, there's usually some type of local structure in the model. So not all variables depend on all values. And this is called the local CSIs of the network. So if we consider all parents of some variable except one specific parent of this vertex, then we call these local CSIs. Of course, they can be more general CSIs as well, but the local CSIs are essentially the way that this context-specific independence typically approached, because these are the kind of the ones that are implied by the network itself. So there are many ways to represent CSIs. For example, just standard conditional probability tables or some kind of decision tree. But what we really wanted to do is to kind of emulate the approach that we have in the structural causal model framework. So we want some kind of a graphical model or some kind of a graph to visualize how the causal connections work under this framework. And what we can do is just extend typical directed acyclic graphs or DAGs by adding labels to them, where the labels describe the context-specific independencies. And we call this LDAGS for short. So whenever we have a local context-specific independence, we are going to have a corresponding label on the edge. And what this really means is just that whenever this assignment that appears in the label folds, then this edge is going to disappear or vanish. And here I'm using squares to denote latent variables. So for example, in this graph, if this variable m has the value 1, then this edge would disappear. But if m is 0, then there's still this edge from A to B. Now we can also just use standard DAGs to describe these scenarios by just using the context-specific DAGs. So essentially, we look at the context, we see what value assignments are holding that context, and we just remove those edges from the graph, so we get the context-specific DAG. So here are some examples what I mean by this. So here at the top, we have a context-specific DAG with some labels, and at the bottom, we have some contexts and the corresponding context-specific DAGs. So for example, here on the left, the first one, we consider the context that z is 0. And we can see that for the edge from u to x, we have this label, z is 0, meaning that in this context, this edge is going to disappear. Now, the second context here in the middle, where u is 1, it's a bit different, because if you look at this middle edge here, where we have this label zu is 1, 1, so not 11, means 1, 1 here, we're only considering binary variables. This means that both z and u have to have the value 1 in order for this edge to disappear. So it's essentially an and condition, not an or. So both z and u would have to be 1 in order for this edge to disappear, meaning that only this edge here on the left, which has the label u equals 1, is going to disappear in this context. And finally, if both z and u are 1, then this middle edge would also disappear. Now, another thing that relates to this approach is that when we're dealing with DAGS, then we have a nice and complete separation criterion in form of d-separation, so we can easily connect conditional independence to separation properties of the DAG. But the same is not true for context-specific independence, because there is no complete criterion for, or complete separation criterion for context-specific independence. But we still have some criteria, some sufficient criteria that we can use. For example, we have this CSI-separation criterion, where we simply look at the context-specific DAGs, and if the independence holds there, then we are going to get the corresponding context-specific independence in the LDAG. But this is very weak, because this doesn't quite often capture all of the CSIs present in the graph. So here's an example of how you might apply this criterion. So we're interested in determining if x is actually independent of y. And we have two contexts, either a is 1 or a is 0 that we need to consider, because they're the only labels that appear in this LDAG. So it's quite obvious that if a is 0, then this edge from z to y is going to disappear. And now if we look at this context-specific DAG, we have a collider here from, or z is a collider on the path from x to y, meaning that these would be d-separated in this corresponding DAG. And similarly, if you look at the context where a is 1, this edge from x to z is going to disappear, and now there are no paths from x to any other variable, so essentially x and y would again be independent. But just because they're independent in each of the contexts, it does not necessarily mean that they're always independent. So we still need to somehow combine this contextual information. And we can do this by noting that actually x is also independent of a. Then we can get an independence of y and a. And from that, we actually get that x and y are independent. But what about causal effect identification? Now we basically have all the tools that we had in the SCM framework, that we can connect the graphical world with the probabilistic world. But how would we go about identifying causal effects? And here we start from something very simple, with the basic ID scenario. We're not going to consider multiple distributions. We're just going to assume that we have the joint distribution of the observed variables, and we are interested in a causal effect of one variable on another, with possibly some conditioning variables. Now, there's still something to consider. First one is that how are we going to handle interventions in this when we are using LDAGS? The second thing is that can we actually do this fast? So can we find a nice and fast algorithm for this? And the third consideration is essentially what I mentioned a bit earlier, that is the CSI separation criterion really enough? Now, I'm not going to spend too much time on the number 3 here, because it's a bit technical, and in essence, the answer is no, it's not enough, because we don't have a complete criterion, but we can still find some stronger criteria than the CSI separation to use. But I'm going to focus on the problems 1 and 2 here in this talk. So let's start from the interventions. And this is actually quite nice when we're dealing with LDAGS, how this works. So what we're going to do, or actually before going any further, it would be nice to imagine how this works when we're dealing with the standard structural causal models. So interventions that target variables, they essentially, when you think of them graphically, they remove the edges that are incoming into that particular node. But when we're dealing with LDAGS, we already have this mechanism kind of inherently built in to the whole LDAG because we have the labels. So essentially what we need to do is just add a new node, which we call intervention nodes, that are going to represent the effects of these interventions. And then we just need to modify the labels of the LDAG so that the incoming edges are going to disappear whenever this intervention node is enabled. And this is really nice because this enables us to essentially get rid of the do operator entirely, and we can just operate on like normal conditional distributions. So essentially, when we would normally write do x, instead we write x and I of x is 1. So meaning that we have observed x, but it's under the scenario that it was actually intervened on. So here's an example, and one issue here is that the labels really become complicated quite fast when we need to add these intervention nodes. So the LDAG itself becomes a bit messy and perhaps a bit hard to read. So this is the same LDAG that I used to represent the context-specific DAGs. And now if we add an intervention node for each variable, we're going to need to modify the labels accordingly. So basically what happens here is that we have the original labels on the left separated by a comma, and here the asterisk means that the intervention node can attain any value. So what this means is that these edges still need to disappear under these original contexts and also when the intervention nodes are enabled. Okay, so what about the second issue? Now we have the tools to describe the interventions, but what about the polynomial nature? Can we actually find a fast algorithm? Well, unfortunately, we showed in our paper that this problem is actually NP-hard, so the decision problem of deciding if this basic identifiability problem from just the joint distribution, whether it's identifiable or not, it's NP-hard for LDAGs. So this essentially motivates the search-based approach also in this context-specific independence scenario. And the proof is quite the same as many other NP-hardness proofs, that you just pick a problem that you know to be NP-hard and show that you can convert one problem scenario of this into the other. Okay, well now we're just lacking one more tool, so we can describe interventions. We have a separation criterion, but how do we manipulate our distributions? How do we try to solve these identifiability problems? In the structural causal model world, we had DAGS, but DAGS doesn't care about the labels or the local CSIs or any other form of CSIs. So what we need to do is construct a whole new type of calculus that accounts for this context-specific nature of the LDAGs. And we call this calculus CSI-calculus. And what it includes is just standard probability calculus, so marginalization, conditioning, and the product rule. Then we have manipulations through the CSIs. And as we saw earlier, basically, we no longer need kind of the do operator. So what this comes down to is we just use context-specific independence to accommodate for the three rules that we would have in the standard do calculus. Then we're going to need some new rules that deal with these context-specific cases. So we need essentially case-by-case reasoning, and sometimes we might need to deal with these variables without them having any value assignment. So we sometimes need to combine the contexts together. So here are all the rules. I won't spend too much time on this. It's kind of simple, really, when you go through it. So the rule 1 essentially captures do calculus, or the entirety of do calculus, basically in the form of context-specific independence. Then rules 2, 3, and 4 capture the standard probability calculus, as I said. And then we have the new rules 5 through 8, which essentially deal with this context-specific information. So for example, here, as we're dealing with binary variables, we might be able to switch from 0 to 1 and vice versa, or we might be able to combine them. So if we know the distribution for both 0 and 1, then we know the full marginal without the assignment. Or we might be able to get, if we know the full marginal, then we also know the case for 0 and 1 and vice versa. Okay. So we also showed that, yes, this is actually so that we lose nothing when we transform our calculus into the CSI calculus. So anything we can do with do calculus in the structural causal model framework, we could also do with CSI calculus. So we really don't lose anything with this by using this calculus, even in the structural causal modeling framework. But even when we have this calculus, we still don't really get rid of the problems with do calculus, that we don't know in what order should we apply these rules, or even if we don't manage to identify the effect, then that doesn't really mean that there wouldn't exist some other way to apply these rules to reach identifiability. And because there's more rules, we now have 8 rules instead of the 3, or if you want to count the probability manipulation 6 in the structural causal modeling framework. Then doing this by hand is very difficult because you need to evaluate the CSIs and take into account more rules than you would otherwise. So once again, we come to the search-based approach. It's essentially the same thing as we had for the general identifiability problem, but instead of operating on DAGS, we're going to operate on LDAGS. And instead of using do calculus, we use CSI calculus. And it works exactly the same way. We only derive identifiable distributions, but there are some additional tricks in this case that we can do compared to the structural causal modeling world, because we don't actually have to consider every possible context. We can kind of see, if we look at the context-specific DAGs, then we might find that actually under different contexts, some of these context-specific DAGs are actually the same. So we only need to find kind of the unique contexts. So those that produce unique context-specific DAGs, which can often help very much, because when you have lots of binary variables and you consider the different value assignments, then the possible combinations kind of explode very quickly. So anything you can do to reduce the search space here is going to make the search a lot faster. And here also you can use search heuristic to make some improvements in the speed. Okay, let's look at some examples how this might work. So this is a very simple example that we had in our paper where we want to identify essentially b, y, do x, but in our LDAG notation, it just be y given x and the intervention node enabled from the joint distribution of ax and y. So variable L here is going to be latent. And you can do this by hand. And if you look at this formula here at the bottom, it's not too complicated. And it's actually quite intuitive if you look at it. Because if you consider the context where a is 0, then you see that actually this confounding path through L is going to disappear because of this label here where a is 0. So this edge won't exist there, which basically means we're just going to get a conditional distribution. And similarly, in the other contexts, there is actually a bit stronger independence that we don't even depend on x anymore. And we just get the full formula by combining these two formulas together. Well, it may look simple when you look at this end result, but if you look at the actual search tree, so what the search is doing in order to get this result, it really becomes quite of a mess because you need to essentially get all the blocks. You need to essentially what you need to do is to essentially identify the effect in both contexts. By context here, I mean in terms of A, so either A is 0 or A is 1. And then you need to actually see if you can even combine these two formulas together, because that's actually usually the difficult part, that you may be able to identify the effect in both contexts, or we might not even need to consider binary variables. I'm just using binary variables here for simplicity. But you may need to then determine if you can actually combine the formulas, which happens here as well. But yes, even in simple scenarios, the search paths become very difficult. And this is just the part that results in identifiability. Of course, the search is not going to know the correct path from the get-go. It's going to explore the search space, and eventually it will reach the identifiability result. Now, another interesting thing that often happens in this context-specific independence is that the formulas in the different contexts before they are combined actually resemble some of these known identifiability results in the SCM world. So for example, in this graph, once again, if we consider contexts in terms of this variable A, we are going to get a backdoor formula in one context and a front door formula in another context. And the final formula actually combines them. So here at the bottom, you see that in the context where A is 1, we have this backdoor type formula component here. And in the context where A is 0, we have this front door type expression at the bottom. So this is some kind of personal curiosity of mine that why does this actually happen? But I don't think this really ever happens in the structural causal modeling world. But when the graph is essentially changing between the contexts, then the formulas can also change accordingly. Well, of course, we proved some properties of this search and kind of investigated at that how fast it is. So how large problem instances we can actually consider. And it works quite reasonably well if we consider kind of typical scenarios that we have in literature. Of course, in inference literature, we don't need to consider too large models. But of course, because it's just a search algorithm, it's going to be very slow and it's going to quickly become quite impossible to apply for large graphs. But up to 10 nodes, you can get a result in a reasonable time, under 30 minutes or so. And this does not include the intervention nodes. So 10 actual observed nodes. We also tried another approach. So I mentioned this fact about how you can make the search faster by combining the contexts. So we compared against this, where we have essentially another variant of the CSI-calculus, where we don't ever combine contexts. So we always assume that every variable has a value assignment to either 0 or 1. Unfortunately, this approach of combining the context is much faster, so there really is some benefit doing this. And of course, you can also use this in a scenario with no labels, then it's going to just essentially be the same then as the do search that I showed earlier in the presentation. Now there's some open problems related to this. So one thing that would be nice would be to get a complete separation criteria, because this is something we have in the structural causal modeling world in the form of the D-separation. And this is something that does not yet exist as far as I know for LDAGS. Because if we had this, then we may be able to show that CSI-calculus is actually complete, at least for this simple problem where we just have the joint distribution. And as I mentioned, there's really nothing that forces us to use binary variables. It's just for the simplicity of the presentation, so you could easily generalize this approach to categorical variables, for example. And perhaps if we have these, then we could maybe find some criteria or some additional criteria to help the search be faster. And similar to the general identifiability problems, we could maybe start including some of these more advanced features like missing data also in this world where we have contextual information. And even though this problem is NP hard, that doesn't really mean that there couldn't be something better than a search-based approach. And I think some work has been done on this that takes advantage of the context-specific DAGS in order to get some additional identifiability results a bit faster than this search-based approach. But it would be nice to have a general algorithm that would be also, well, better than this search-based approach. Okay, well, that's basically the end. Here are some references. So first, 2 papers here are the papers I mentioned in the beginning about this do-search algorithm and this context-specific approach. Third paper on this list is this paper by Mohan and Pearl that contains some results for the missing data scenario and some examples on why you really need do calculus for causal missing data problems. If you're interested about context-specific independence, then there are some papers here. So first one is, well, about basically the context-specific independence itself. And the second paper is more focused on their representation via these labeled direct acyclic graphs. And finally, if you're interested about the data diffusion problem, we have this paper by Brembo and Pearl, and then also this, I guess this is the original paper about context-specific independence in Bayesian networks by Boutillier et al. Okay, thank you very much.